Good morning. Welcome to another edition of Chemistry on the Fly with Mr. F. Today we're going to be talking about Chemistry of Light Part 2, 6.15. We're going to bring back some old friends today, but let's review a little bit. So we saw light yesterday because it looked like three different types. So the first thing was a ray, and that was put out by the Greeks back in BC times, Pythagoras, Euclid, and Ptolemy. And they all thought it was light was a ray. Now, that is really coming back to what Newton and Einstein said much later on, that it was a particle, but we'll come back to that in a second. Now, Huygens and Planck in the 17th, 1690s, 1700s, and then Planck again in 1900s were convinced that light was a wave, and it looks something like that. And then, as I said, Newton and Einstein in 1704 for Newton and in 1905 for Einstein thought that light was a particle. Now, even today, scientists still haven't decided whether it is a wave or a particle. Again, the rays are more continuous particles, so that's still the same idea. All right, so we're going to bring back some old friends today. So the first thing we're going to do is bring back, and we're going to take a little bit more of an elementary level, and we're going to bring back our old friend Niels Bohr. Now, if you remember, the Bohr diagram started off with a proton, for hydrogen at least, a proton in the nucleus, in the center, and then one ring for the one electron for hydrogen. And we have, I'm still showing the electron cloud around the whole thing. Now that was the idea of Niels Bohr. Now, Niels Bohr did a whole bunch of demonstrations and experiments on hydrogen and found out that it didn't just have one energy level. It turns out that it had six, actually technically it could have infinity number of energy levels, but it rarely gets past six. So we're going to just keep it at six. Now, what do I mean by that? Now, you notice the picture here shows that energy levels, only the first energy level or the innermost energy level has an electron in it. But that doesn't mean that the other electrons or other energy levels can't have an electron in them. And we'll see how that happens in a second. This is another demonstration from PHET from the University of Colorado. What we see here is a demonstration where I have a hydrogen atom, so you can see the red nucleus with a bluish electron, and you can see that it has six energy levels. So you can see it's rotating around, and what happens is as it receives energy, it then jumps to a higher energy level. It doesn't like that energy level, so it wants to come back down, and in doing so, it actually releases some energy. So on the right-hand side, you can actually see what's going on. So currently it's at level 1, jump to level 3, back to 2, back to 1. And when it does that, it gives off a certain wavelength of energy. So it's at 5, went to 1, gave off some energy. Now on the bottom right-hand corner, we can see what type of energy it gives off. So we see that it has some ultraviolet in the 92 nanometers. And then we see somewhere probably around 400 or so. We see maybe 420. We see some violet. We see a little bit of blue, maybe about 430. And then about maybe 480, we see a teal color. And then somewhere around 650, we see a huge amount of red. So when we look at the spectrum for hydrogen, we would expect to see some red, teal, blue, and violet. And you can also see as you go further out, we would have some infrared at 780 and then some at even higher than that. So we can see that this is where our spectrum should look like. Obviously, we can't see the ultraviolet or the infrared, but we will see, and we should see, a very strong red, a very strong teal, a blue, and then a violet. Let's take another look at what we just saw in the PHET demonstration. So I have a hydrogen atom with a one electron around its first energy level. Now, this is called the ground state. This is where it likes to be home. Now, there's going to be some time, though, when a packet of energy, which we've called or we will call a photon, is going to come in, and it's going to knock that electron into an outer energy level. Notice it's no longer in energy level 1, and I have it shown in energy level 4. This is actually called the excited state. Now, electrons don't like to be in this excited state, so eventually what will happen is they will give off another photon of energy and jump back to a lower state. So that's what we just saw. So let's see if we can explain that again. So we start out in the ground state. Now I'm not going to animate the electrons this time, just because it gets a little too confusing, but I have the ground state. So the electron is in the first energy level. A photon comes in. Again, a photon is going to be a packet of energy, and this is really what Einstein was talking about as a particle. And a photon comes in, it's going to hit into that electron on the first energy level, bump it to an excited state in the fourth energy level in this example, and then eventually it's going to sit in that excited state until it wants to give off that photon, and then it will jump back down to the ground state where it prefers to be. Now, that's how it looks like from the electron level. Now let's see what happens actually when we get a little further, take a little step back, and we still see that they're going to have some excited states, and we'll talk about that in a second. And we're going to look at something called the emission spectrum. Now, we're going to bring back our guy from our videos from yesterday, our PHET demos from yesterday, and right now he's looking out into dark space and he's seeing a basically black, because remember, black is the absence of color. Now, if I bring the sun in and the sun puts out a white light, he's eventually going to see white. Now, what we're going to do next is something pretty cool. Now, I wish I could show you this in class, and I normally would, but we're not there. So we have these cool glasses that we're going to put on our guy, and these are called diffraction glasses. And these glasses allow the light to come in, and instead of being just a solid white light, it actually diffracts all of the light into its spectrums, very much like the prism on the Pink Floyd album did. So it took the white light in and breaking it down into the colors. Now sun and produces a white light, and white is going to be a combination of all colors. We learned that the other day. So if you look at what he sees now, he's actually going to see a continuous spectrum. So we see that it actually goes from red, blends into orange, and then blends into yellow, and then blends into green, and then blends into blue, and then violet. That's called a continuous spectrum. Now, we can look at some other things that are not continuous spectrums, and we'll find out what that's going to be in a second. Now, I have this cool, basically it's a lamp that I plug in, and I have these pretty cool little bulbs that have different gases in them. And in this case, we're going to look at hydrogen first, but I have it hydrogen in there, and when I put it on, it actually gives off a pinkish color. So if I am looking at this, I would see, just like the guy sees, a pink color. Now what's happening is that the electricity in this lamp is exciting the electrons, and they're jumping to higher energy levels. They don't like being there, so they jump back down and they give off other photons. And that photons, sometimes they're ultraviolet, and sometimes they're visible, and sometimes they're infrared, for at least for hydrogen. So in this case, we're looking at the photons that are visible. And then if I put on these cool glasses, whoa, I'm not seeing a continuous spectrum this time. This is actually a line spectrum. And you can see we found this out when we were looking at the demonstration, where we had a very strong red line, we had a teal line, we had a blue line, and we had a violet line. We saw that in the demonstration from the PHET demo. Now, this is called a line spectrum, and you can kind of see why it's called a line spectrum because it shows the various lines. Now, this line spectrum happens to be good for hydrogen. Now, what would happen though, if I took a different bulb, and this time it's filled with helium, and did the same thing? Uh-oh, it's actually not showing pinkish anymore. It's now showing more of a white, kind of a yellowish white. Well, when I put the cool glasses on, it's actually going to change into a different line spectrum. And you can see that this one has a very, very strong yellow. It has some blues and greens and some teals and a red line as well. And then adding all those together, we get this kind of a tannish white light, yellow white light. Now you would think, well, that's pretty cool. So I have one for helium, one for hydrogen, and they don't look very much alike. Well, it turns out that they're not alike at all. So if we look at some things, so this was a continuous spectrum for the sun, and if we looked at hydrogen, this is what the hydrogen spectrum would look like, and it's called a spectrogram, okay? And helium looks a little different. Some of the lines are matching up, but not really close. The blue, the teal, or not the teal, the violet lines are close, but that's it. But then if I start looking at other things like neon, whoa, neon is really different. And if I look at a metal, let's say sodium, I'll see that sodium actually looks kind of very plain. It turns out that each of the elements have their own signature. Now, you may have seen on a crime show where they say, oh, we use a spectrometer to analyze the sample on the guy's shoe, and he was able to find out that, oh, they only have this kind of sample in this plant. They manufacture something. And what they can do is they actually use a spectrometer. They heat up the element, and then it gives off a color, and that color spectrum will identify what element it is. Now, it's not a very easy process, and a lot of times they make it, in the TV shows, they make it as though it just happens in a minute, but that's just for time's sake. But that is actually how some crime scenes are actually solved. So that's it for today. Well, oh, hi, Niels. What's going on? What do you think? What do you got to say? Oh, I like your new glasses. What do you have to say about that? Lit. All right. Well, that's all we've got today for Chemistry on the Fly. And as always, have a great day.